Hey everyone, and welcome to this explainer. I am so glad you're here today because we're going to dive into something pretty wild. We're talking about one of the most transformative, yet completely invisible, forces that powers our entire modern world. We're going to explore electromagnetism, and specifically how we've managed to harness it to literally create motion. So, think about this for a second. What do your kitchen mixer, a super precise robotic arm on a manufacturing line, and a massive industrial power plant all have in common? I mean, on the surface, they seem completely unrelated, right? But if you strip away the exterior, you'll find they all rely entirely on the exact same underlying engineering marvel to get their jobs done. Yeah, you guessed it, it's the electric motor. At its most basic level, an electric motor is just an electromechanical device that takes electrical energy and converts it into physical mechanical work. Now, if you've ever studied generators, you know they do the exact opposite, right? They convert mechanical work into electrical energy. But here, we're taking electricity and using it to create continuous motion. And while it's true that no conversion is 100% efficient, because, heat and friction will always take their cut, this specific process is literally the absolute backbone of modern industry. To really get our heads around how this works, we're going to take a quick taxonomy tour of the motor kingdom. We'll start by looking at the basic anatomy of a motor. Then we'll check out DC motors, both brushed and brushless. After that, we'll dive into stepper motors, and finally, we'll wrap things up with the really big guys, three-phase AC motors. All right, let's kick things off with Section 1, Anatomy of a Motor, or as I like to think of it, the magic of magnetic fields. At the end of the day, every single motor we're going to talk about relies on this continuous, invisible game of magnetic tag. It's just a constant dance of attraction and repulsion. To pull this off, a simple motor needs a few basic components. You've got your power source, which is usually DC for a simple setup. You need a field magnet, that could be a permanent magnet or an electromagnet, and then you have the part that actually moves, the armature or the rotor. So, how does it all come together? Well, imagine taking a conducting wire, making a little loop, and placing it right between two magnets. When you run electricity from your power source through that loop, boom, a magical thing happens. The loop itself becomes an electromagnet. Suddenly, one side of it is attracted to the north pole of your field magnet, and the other side is pulled toward the south pole. This attraction is what forces the loop to physically move. Now, to keep it rotating continuously so it doesn't just get stuck in one spot, we use a commutator and brushes. These conduct the current to the moving parts and constantly flip the magnetic field. The end result? The axle spins, and you've got mechanical output. But wait, here's a really fascinating twist. As that loop spins through the magnetic field, it actually acts like a mini generator. It generates its own voltage that pushes back against your original power source. This is called back electromotive force, or back EMF, and it's absolutely crucial. It naturally regulates the motor so it doesn't just accelerate infinitely until it literally tears itself apart. Pretty elegant, right? Moving right along to Section 2, DC motors, specifically the brushed and brushless varieties. Permanent magnet DC motors are incredibly popular, especially when you need strict control over speed or torque. Honestly, it's just notoriously easier to implement control systems using DC motors compared to their AC counterparts. Within this category, we're really looking at two main flavors. First up is the traditional brush DC motor. This uses exactly what we were just talking about: wound coils of wire on the rotor, fixed magnets on the stator, and mechanical sliding electrical switches. Those are the commutator and the brushes to constantly rotate that magnetic field. Then, on the flip side, we have brushless DC motors, or BLDCs. Now, these function on the exact same underlying principles of magnetic attraction and repulsion, but they completely ditch the physical wear and tear mechanical brushes. Instead, they use active electronic commutation. You do need drive electronics to make them work, but because BLDCs eliminate all that physical friction and the electrical arcing you get with mechanical brushes, they boast significantly higher efficiency and a much, much longer lifespan. That massive boost in efficiency is exactly why brushless motors are the absolute standard in everything from consumer drones to electric vehicles today.
Okay, on to Section 3, stepper motors. Think of these as the precision dancers of the motor world.
The absolute defining feature of a stepper motor is right there in the name. Its shaft rotates by performing steps. It moves by a fixed, exact amount of degrees. Because it's so locked in, you don't even need a sensor to know the exact angular position of the shaft. You literally just count the steps. To understand how it gets that kind of precision, we have to peek inside. Surrounding the stationary stator, there are teeth with coils wired around them. In the center is the rotor, which in this case is a variable reluctance iron core, and it's cut into a very specific, jagged shape. By changing exactly which coils on the outside are energized, we can force that iron core in the middle to physically snap into alignment with the newly created magnetic field.
Let's walk through how this builds into predictable, continuous movement. Step 1. We energize coil A. The iron rotor immediately snaps into perfect alignment with the magnetic field produced by that specific coil. Step 2. We turn off coil A and we energize coil B. The rotor is now forced to rotate, let's say clockwise by exactly 60 degrees, to perfectly align with this new field. Step 3. We energize coil C, and the rotor chases the field again. By supplying these different phases in a highly precise sequence, we are literally pulling the rotor around in incredibly precise, measurable increments. It's like clockwork.
Which brings us to our final group in Section 4, three-phase AC motors, covering both induction and synchronous types.
So, while steppers give us amazing precision, sometimes you don't need precision. Sometimes you just need raw, massive power. That's where three-phase AC motors come in. These are the heavy-duty workhorses of industrial applications and large alternating current power networks. Most of these AC motors, actually up to 90% of them, are induction motors, and they use something wonderfully called a squirrel cage rotor. It's called that because of its cylindrical core with parallel slots filled with copper or aluminum bars connected at the ends by heavy rings. It kind of looks like a little exercise wheel for a rodent. Now, the really crucial point here is how this rotor moves without any direct electrical connection from the stator. When the stator is supplied with a three-phase AC supply, it produces a rotating magnetic flux. As this magnetic flux sweeps across the bars of the squirrel cage, it induces a voltage right inside them, very much like how a transformer works. Because the cage is a closed circuit, a current starts flowing. And thanks to Lenz's law, this newly induced current creates its own magnetic field, which tries to fight the change. It tries to reduce the relative velocity between itself and that rotating stator field. So, in simple terms, the rotor gets dragged around, desperately trying to catch up to the rotating stator field. But here is the catch. It can never, ever actually catch up. This permanent game of cat and mouse is known as slip. The rotor absolutely must spin slightly slower than the magnetic field so it can keep cutting those flux lines, otherwise the induced current would just drop to zero. So while they are incredibly robust and super reliable, this necessary slip does mean induction motors take a slight dip in electrical efficiency.
The other major player in the AC motor world is the synchronous motor. If induction motors are the heavy-lifting workhorses constantly chasing the field, synchronous motors are the perfect timekeepers. They're typically built in much larger units than induction motors, and they are the absolute go-to choice when you need constant speed industrial applications.
So let's put these two AC giants head-to-head for a second. Induction motors are asynchronous. They depend entirely on that relative speed, that slip, between the rotating magnetic flux and the static rotor conductor to generate the induced current. The rotor is always being dragged just a little bit behind the stator's field. Synchronous motors, on the other hand, play by different rules. At a steady state, the rotation of their shaft is perfectly exactly synchronized with the frequency of the source current. There's no lagging, there's no dragging, just perfect harmony with the alternating current supplying it. And because synchronous motors don't rely on slip, and they don't have to draw induction current into the rotor just to create a magnetic field, they operate at a much higher efficiency. That's what makes them so ideal for massive, continuous industrial loads where literally every single drop of energy counts.
So, there you have it. From the simplest little toys using brush DC motors to the ultra-precise stepping of a 3D printer, all the way up to the massive synchronous motors keeping our heavy industries churning, none of it, and I mean none of it, would be possible without the magic of electromagnetism. We've literally figured out how to command an invisible force, taking the simple attraction and repulsion of magnets and turning it into the physical motion that drives human progress. It really does beg the question. If we can harness magnetic fields to precisely rotate everything from tiny robotic arms to massive industrial turbines, what invisible forces are we going to engineer next? Thank you so much for joining me for this explainer. I really hope you walk away today with a deeper appreciation for the invisible hand of the electric motor. Keep learning, stay curious, and I'll see you in the next one.